Welcome back, everyone. In this lecture, we're going to talk about hypothesis testing. And as you will see, hypothesis testing lays the groundwork for inferential statistics. It's what's going to allow us to see whether or not information we get from a sample can be used to tell us something about the larger population. So in this particular lecture, we're going to go over the purposes of hypothesis testing. Then we're going to walk through each of the steps of hypothesis testing and then wrap up talking about the difference between one versus two-tailed tests. The reading for this particular lecture is Chapter 4, Module 8 of the 4th edition of our textbook. Now, the number one thing when we think about what is the purpose of hypothesis testing is we want to know, do we have a rare or a common sample? We talked about in our example with the coconuts on the island and the sampling distribution of the mean. And we said, what's the likelihood that we would, by getting one single sample off that island, that it would be reflective of or representative of the larger population? And that's kind of what we're thinking about with hypothesis testing is, do we end up with a rare or common sample? We get access to one particular sample. We don't expect it to be a perfect representation of the population, but sometimes we find a sample that is so rare that we think maybe it's more likely to have come from a different population. Now, what do I mean by a different population? Well, if the particular sample we have is so rare that it does not appear to have come from the population we hypothesized it to come from, then we say maybe we have seen a significant change, a significant effect, or a significant difference in whatever phenomenon we're studying. And that's the goal of science in many ways. We want to see, does a particular pill shorten if you take it, does it shorten the duration of your symptoms? If we want to see a change in law enforcement strategy, does that reduce the amount of crime? Things of that nature. So we're looking for those rare outcomes. Those are actually the exciting things in science. Now, when we look at hypothesis testing, there are 6 basic steps. And then I notice you'll see that there's a 7th step listed here, but we'll get to that in a moment. So those 6 basic steps are going to follow us through the rest of this course. So as we go from one inferential test to another, we're going to still be thinking about each of these 6 steps. So any research question or hypothesis test has to start with a research question. Once we have our research question, we, as the statisticians, we need to translate it into a statistical or two competing statistical hypotheses. And so we're going to see those 2 statistical hypotheses that we can test against each other. And remember, at the end of any hypothesis test, we're going to have to pick one of those hypotheses. So once we have set up our 2 statistical hypotheses, we need to figure out our degree of rarity. That is known as the level of significance in step 3, otherwise known as alpha. And as you can see, the lowercase Greek alpha denoted there. And we'll talk about how we set that and what that means. Once we have that, that will help us to determine what happens in step 4, which is to determine the critical value of our particular test statistic. Once we have that, we now have the point at which we draw a line in the sand to determine rare versus common outcomes. In step 5, we take our actual sample data and compute our observed test statistic. Once we have our observed test statistic, we can move on to step 6. And in step 6, we compare our observed test statistic versus the critical value that we got in step 4, and that will make our decision. And one of the things to keep in mind is at the end of any hypothesis test is we have to make a decision. And our decision is pretty much either to accept one of the statistical hypotheses or the other. So we cannot have everything and we cannot fail to make a decision. We have to choose one hypothesis. Once we get to that, we will allow ourselves to start to think about the notion of confidence intervals, but we'll save that for the next lecture. All right, so let's take a look at these steps of hypothesis testing. Step number 1, every research study starts with a research question, period. I want to know, does a particular policing strategy reduce crime? I want to know, as I think somebody talked about in class, Do athletes who suffer from CTE, are they more likely to engage in crime? Does taking a particular medicine or pill help to reduce your anger or reduce your symptoms of migraines? Does practicing a certain type of strategy help you perform better on a test? Whatever it is, we always start with a research question. So the one thing for us as statisticians is we need to transform that research question into a format with two possible outcomes. So if I want to know, does having offenders go through a particular reentry program prior to being released from recidivism, if I want to know, does that reduce their likelihood of recidivism, my question becomes, does going through this particular program reduce the likelihood of recidivism? And then I have two answers, either yes it does or no it doesn't. And that's how we have to make sure any one of our research questions starts off with a yes, no, either, or type setup. Once we've established our research question, we can move on to translating those into two competing statistical hypotheses. So in any sort of hypothesis test, there are two possible outcomes. There's either what is known as HO, the null hypothesis, or there's H1, the research hypothesis. The null hypothesis, if it helps, think of the word null. Null means nothing. So whatever your research question is, null hypothesis says, nope, no change, no effect, no difference, doesn't work, nada, nothing. That is the null hypothesis. And we'll see how we write that out. The research hypothesis is the hypothesis that you as a researcher started to go looking for. If you wanted to know, does suffering from CTE lead to anger issues, then if the answer is yes, that's what you're looking for in your research hypothesis. If I want to know, does a particular type of law enforcement patrol strategy reduce crime rates in a certain area, then the answer, yes, it does. That's my research hypothesis. So we have to set up these two competing statistical hypotheses, the null and the research hypothesis, in a way where they are, one, mutually exclusive. What that means is that they can never be overlapping. They can never have any overlap. You have to have either your answer comes out to be the null or it comes out to be the research hypothesis. You can never have the best of both worlds in this case. And two, they have to be exhaustive. Exhaustive means it has to cover all possible outcomes to the research question. And this is why we set up the research question in a manner that looks like two sides of a coin. You've got to either go with one or you've got to go with the other. You can't have both sides, and you've got to cover all possible outcomes. So that's the way we're going to be setting up our hypotheses as going forward with each one of these tests. All right. Step 3 of a hypothesis test is what is known as the level of significance, or alpha. So the level of significance, or alpha, as you can see defined by one of the bullet points, is the degree of rarity required to reject the null hypothesis. Okay, so in order for us to make our decision in a hypothesis test, as I said earlier, we're going to have to pick one of the two hypotheses, either the null hypothesis or the research hypothesis. Well, now we think back to the idea of rare versus common samples. In order for me to say that I have a truly rare sample, I need to know, well, just how rare does it have to be in order for me to call it rare? That's where alpha comes in. Alpha is going to work with us to determine the point at which what is a rare versus a common outcome. So, looking on to the next bullet point, the level of alpha is going to be determined by the researcher prior to conducting a hypothesis test. What that means is we, as the researcher, we get to choose what alpha is. We get to choose the point of rarity or commonality when looking at our sample data. So the typical level that is chosen is 0.05. And as you can see at the very bottom, it says alpha equals 0.05. This is the standard. It will be the level of alpha that we will use for all of our hypothesis tests throughout the rest of the semester. So by saying that alpha is 0.05, what that means is in order for our sample data to be called rare, it will have to be so rare that it ends up out in where there's only 5% of the area under the curve or less for that value to occur. And that, yeah, we'll leave it at that. All right, let's move on. All right. The critical value of the test statistic. All right, step 4, critical value of the test statistic. So once we have set alpha, that will determine what the line in the sand or the dividing line between common and rare happens to be for our particular statistic and our particular statistical test. So what you see here is it says for number 4, critical value of the test statistic. Well, the first test we're going to talk about in the next lecture is the Z-test. And in a Z-test, we've already looked at the Z normal distribution, the standardized normal curve. We've looked at the area under the curve, and this will translate back to that. So we'll start with the Z-test, and I think that will be a nice way to introduce this. But then as we move on to T-test, F-test, etc., all of these also have critical values for any particular hypothesis test. So depending upon the test that you are doing, you need to figure out the critical value. So in step 3, we set up an alpha of 0.05. That alpha is going to help us to determine the critical value for our test statistic. And then as I have said several times, but you can see on the next bullet point, this critical value will serve as the dividing line between rare and common outcomes. So our first example will utilize the Z-statistic. Therefore, the critical value will be referred to as the Z-critical. And you may recall I mentioned it in class, but I'll mention it here and you'll see it in the next lecture without a doubt. The number 1.96. And you may recall when we look at the Z curve and the area under the curve, that value 1.96 was really important to us. So keep that in mind as we go forward. In step 5, now you need to look at your actual sample data and figure out what kind of test statistic you have. What is the observed value of it? Whether it's a Z-test, T-test, etc. You need to look at your sample data and actually compute the test statistic. So going through the bullet points, our sample data will provide us with the information needed to compute an observed value of the test statistic. And you can read the following bullet points. The only time that we in this class will have to hand compute an observed test statistic will be for our first test. That's the Z-test that we'll be doing in the next lecture. After that, we will trust the output and data from SPSS to just read and interpret the observed test statistic. But without getting too far ahead of myself, let's move on to what do we do once we get our observed value of the test statistic. And that leads us to step 6. So step 6 is we now have to figure out what is our decision. And kind of doing a quick recap of what we've thought about with hypothesis testing. It all started with a research question. Does this particular drug work? Does this law enforcement strategy work? Has some particular thing changed? Is there a significant difference between this group and that group? Whatever our research question is, we have set it up into 2 competing hypotheses. We have the null hypothesis, which always says, nope, nothing has changed. Nope, that does not work. Nope, there is no difference between these 2 groups. No, that does not have an effect on something. The null hypothesis is always, nope, it didn't do anything. Our second hypothesis is H1, or the research hypothesis. The research hypothesis is what we usually, as a researcher, are hoping to find. We're hoping to find, oh, yes, this drug did have a positive effect on something, or this law enforcement strategy worked to actually reduce crime rates, or this particular method of anything changed the world we live in, or yes, there really is a difference between this group and that group. That is the research hypothesis. So we have 2 hypotheses, a null hypothesis, no, nothing, no change, no difference. We have a research hypothesis. Yes, there is an effect. Yes, there is a change. Yes, there is a change, or there is a difference. All right. So once we have both our critical value of the test statistic, step 4, as well as our observed value of the test statistic, step 5, we can make our final decision. And in its simplest sense, we start with looking at our second bullet point here. The final decision can be made by. We start with comparing the observed value to the critical value. And that's what we'll start with in our next lecture with the Z. If our observed value is more rare than the critical value, we're going to reject the null hypothesis and choose the research hypothesis. On the other hand, if the observed value is less rare than the critical value, we will determine our outcome to be common, and we will fail to reject the null hypothesis, which is basically saying we didn't want the null hypothesis to happen, but we can't reject it. As we move forward in the class, we're also going to start talking about p-values. And when we look at SPSS data and output, we will be able to examine the p-values for observed test statistics, and we won't have to even really deal with step 4. But we'll get there when we get there. For right now, we're going to look at comparing observed value versus critical value. All right, so just to reiterate, what are the two possible outcomes or test decisions that can result from a hypothesis test? At the end of the test, we can either, 1, reject the null hypothesis, and if we choose this, this means that we are concluding that our research hypothesis is correct. So choice 1, rejecting the null hypothesis, is saying, yes, there is an effect. Yes, there has been a significant change. Yes, there is a significant difference. Whatever you're trying to look for in your research question, we're saying, yes, something is going on. On the other side of it, if we fail to reject the null hypothesis, if our outcome says that our sample is not that rare, our sample is pretty common, we're going to fail to reject the null hypothesis. And if we choose that one, that's the same as saying that, well, we're basically going to go with whatever the null hypothesis said. We're going to, at least for the time being, saying there's no evidence to show that there has been a change. There's no evidence to show there's a significant difference. There's no evidence to show there's a significant effect. So rejecting the null hypothesis is saying, yes, we have found an effect. Failing to reject the null hypothesis is saying, we don't see anything exciting here. There is no effect. Finally, let's talk briefly about one versus two-tailed tests. So both throughout this lecture, in your course textbook, as well as if you look at online resources, you're going to find different interpretations of one versus two-tailed tests. Also, one-tailed tests are also known as directional tests or one-sided tests. Two-tailed tests are also known as non-directional tests or two-sided tests. The idea here, when it comes down to the reality of these, is trying to determine out where do we put the rare areas. So let's look at our top distribution on this slide. You'll notice here it says the rare area under the curve can be in either, oh, that's a mistake, I should probably fix that, but I'll fix it later, can be in either of both tails. That is a two-tailed or non-directional. So you'll notice that what they have there is they have, once again, you may call the number 1.96. They have a negative 1.96 down on the lower left-hand side, and they have a positive 1.96 up on the upper side. And in fact, even using our area under the curve chart that we looked at in class, but as reiterated in this slide, you'll notice that there is 2.5% of total area under the curve below a negative 1.96, and there's also 2.5% of the area under the curve above a positive 1.96. So when you combine those two together, you get a total of 5%. Remember back in step 3 when we set alpha at 0.05. So we're saying that the amount of rare area under the curve is only where there's 5% of area. But in a two-tailed test, we split that into both tails. That's where that negative and positive 1.96 come into play. On the bottom example of the histogram, we see that we have the normal distribution, but this is an example of a one-tailed test. And here, imagine if we said we're only predicting a change in one direction. Well, in this one, we would put all of the 5%, the alpha of 0.05, that 5% of the area under the curve, in only one tail. And so you'll notice that here, the value, the critical value becomes 1.645 because that's a point at which there is 5% above it, 95% below it. Because in the realm of research, we want to capture good outcomes, but we also don't want to miss negative outcomes. We typically work with two-tailed tests, and that's what we're going to work with in this class. So you can see the note on this slide, it says we will only be doing two-tailed tests in our class. So one-tailed, you can read about them, you can learn about them, but as far as the examples we will walk through in this class, we're looking for two-tailed tests. We're looking for significant outcomes in either direction. But note, looking at these two histograms, you can see it does change that sort of dividing line between common and rare. Take care.